Measurement. So in this lesson, or by the end of the lesson, students should be able to identify and measure electrical power. So we're going to focus on this final piece, which is electrical power. Okay, so electrical power. Let's spend a little bit of time kind of focusing on exactly what this is. So power is measured in what are called watts. So power is measured in watts, and essentially what watts are voltage multiplied by current. Okay, so we want to kind of think about this and break it down piece by piece. So when we're talking about power, we're basically starting to look into the area of energy. So what is energy? So energy is the ability to do work. So in order for work to be done, we need energy. So for example, like if we wanted to take an object and we wanted to apply a force and move that object a distance, we would be doing some work on it. And in order to do that work, we would need what's called energy. So for example, if you, for example, physically lift up a box and move it from one side of the room to the other, you are using chemical energy in your body, and that's being converted into energy that's needed then to move the box from one point to another. So that's what energy is. So energy is basically the ability to do work. And we measure energy using this a way called this the metric, if you like, or unit that we use to measure energy is what's called the joule. Now, energy is kind of a funny kind of phenomena. So everything in the world is made up of matter, which is made up of atoms, and energy. So basically, energy is like the stuff that gives matter, that animates matter or makes it do the things that it does. And there's this principle in relation to energy. So energy cannot be created or destroyed, but it can be converted from one form into another. So what happens is we're taking energy and it can be changed from one form into another. And that's essentially what power is. So power is basically you're taking energy and you're converting it from one form into another. That's when we talk about power, that's what we're talking about. So a way to think about power, which is measured in watts. Okay, so this is what's measured in. So watts. So basically, watts are joules per second. So another way to think about it is it's energy being converted from one form into another per second. So that's kind of like what that's what watts and power is looking at or is measuring. So we talked in the last lesson about the electron. So if we take electricity, for example, we have this like tiny subatomic particle called the electron. And basically, if we apply a force, so for example, if we apply a positive force, what's going to happen is this electron is going to move towards that positive force. And this is what we call what's known as voltage. And another way to kind of think about voltage then is to think about it's like the bigger the voltage, the more energy the electron has. And the bigger this positive force that's attracting or pushing the electron through a conducting material, the bigger the voltage. Now, another way to kind of think about this as well, when we're talking about uh, electrons, so for example, when we talk about electrons moving through a piece of wire, electrons are extremely small subatomic particles. So what we can do is we can think about, so if we think about, for example, a dozen eggs, that gives us a quantity of eggs that we can look at. So in a similar way, what we can do is we can use this idea of what's known as the coulomb. Okay, so we have this thing called a coulomb. So this coulomb. So basically what a coulomb is it's the charge on a massive number of electrons. So because electrons are so small, every second at a particular point, there's a huge amount of electrons moving through, for example, a conducting material. So just to kind of put it into context, if we were to, like the amount of electrons that, or the amount of electrons that make up a coulomb of electrons, we're talking about 6.2 multiplied by 10 to the power of 18. So that's going to be 6, 2, and then you're going to have 17 zeros after it. That's how many electrons, if you like, make up this idea of what's known as a coulomb. So when you have a coulomb of electricity or of electrons, that's how many like individual electron negatively charged particles you're going to have. And when we talk about current, so we talked about how current is if you have a conducting material like this and you stand here like this, current is like every second, okay, the amount of electrons that pass this particular point. So to get even more detailed on it, and we measure current in amps. So 1 amp is basically 1 coulomb per second. So in other words, you have 6.2 multiplied by 10 to the power of 18 electrons every second moving past this point. That is 1 amp. And if you take that amount of electrons, okay, so that coulomb of electrons moving through, when we talk about voltage, so 1 volt, so that collection of a coulomb of atoms will have 1 joule of energy. Okay, so that's the kind of more detailed way at looking at, for example, electrons and their ability to do work. So basically then, if we take these two things, okay, so current is, for example, a coulomb amount of 1 amp is measured in amps, so 1 amp is a coulomb amount of electrons moving past a point in 1 second. Voltage is basically the amount of energy per coulomb of electrons moving through a point. So when we multiply these together, what we get is a watt. So basically a watt then is 1 joule per second. Okay, so 1 joule of energy per second. So that's kind of like how all of these individual parts that make up electricity and make up power, how they all kind of come into contact with each other and give us a way at measuring, for example, the power that is needed in order to get some specific type of work done. So if we think about the electron, for example, so here we have, so imagine this is like a conducting material like copper. And imagine then you have like a coulomb amount of electrons. Okay, so you have 6.2 multiplied by 10 to the power of 10 to the power of 18 electrons. And what they're doing, so you have 1 amp of electrons moving through this conducting material. So copper itself is made up of atoms. And what happens is when electrons move through copper, for example, they don't just move through in a straight line. What will happen is they will hit against and bounce off the atoms that are, so imagine we have this positive charge here, this positive terminal in the battery, and it's creating a potential difference. So what's going to happen is it's going to kind of make its way through the coulomb of electricity is going to make its way through the piece of copper wire. So it's going to go through kind of like, this path. It's going to bounce off each of the atoms inside the copper wire. And what's going to happen then is it's going to make the wire, it's going to make the atoms in the wire vibrate. Or another way to think about it is it's going to make the atoms in the wire do some work. Okay, so it's going to exert a force onto each of the atoms. So, and that vibration, okay, will be felt as heat. So what you have happening is this principle here. So energy cannot be created or destroyed. It can only be converted from one form into another. So if you imagine you have this coulomb of electrons, okay, and they're moving through the wire, they're being attracted towards this positive charge. They're going to bounce off the atoms inside the copper wire, and as a result of that, they're going to cause the atoms in the wire to vibrate, and as a result, they're going to give off heat. But what's happening is the electrical energy that's in the energy that's in the electrons from their movement, okay, so some of that energy is being transferred into the atoms, and then that's being converted into heat. So what you're getting is this conversion of one form of energy, which is electrical energy, electrical energy is being turned into heat energy. Okay, so it's being lost as heat. So these electrons will move through the wire, and you'll get this coulomb of electrons that are being moved through the wire. And these electrons, what they're actually doing is they're doing work, so they are, and they're causing the wire, for example, to heat up and to vibrate. Now, what can happen then is we can use this movement of electrons to do some useful work. So for example, if instead of using copper, we use this material called tungsten. So this is what's inside light bulbs. So imagine you have the filament like this. And again, what you're going to have is you're going to have, let's say, a coulomb of electrons moving through this piece of wire and coming out the other side. And as it moves through, as the 6.2 multiplied by 10 to the power of 18 electrons, then that big flow of electrons moves through the piece of tungsten, and it bounces off all the atoms in the piece of tungsten. The piece of tungsten will get really hot. And what you're going to get then is you're going to get electrical energy being turned into heat energy, and you're also going to get it turned into light energy. So this bulb, if you like, filament bulb, will get really hot, and some of that electrical energy will be converted into light energy, and it'll shine out through the filament. But a lot of it will be turned into heat energy, and that heat energy will just be transferred into the room. So that's kind of like a waste, so it is. Now, if instead it is, so imagine it's an electric heater. So imagine you have like something like this, and it has heating bars inside it. So again, it's the same principle. You have these bars, for example, you can think about this is what's going on inside each of the bars in an electric heater. You have the electrons moving through it, causing the atoms in the material that make up the heating bars in the heater to vibrate. They get hot, and what they do is they radiate heat. Again, you have electrical energy being converted into heat energy. And then we can even go right back. We can go back, let's say, like where is the electric? So when we plug in a socket, for example, where does that energy come from? It comes from, for example, power plants. And what you have there is you might have something that's like this, like a turbine. And what will happen is you will have steam, okay, which has a lot of kinetic energy. So kinetic energy is the energy the steam particles have from movement. And what will happen is those steam particles, that energy will be transferred into making the turbine turn around. Okay, it's turned into kinetic energy, and then that turning of the turbine then will be converted into electrical energy. And that electrical energy then is just the movement of electrons. And that electrical energy then can be used to do all kinds of useful work, like light a light bulb, like make a heater heat up. If you take a toaster, for example, the same principle. You have this movement of electrons. It causes the elements in the toaster to vibrate. When those elements in the toaster vibrate, they get hot, and that heat energy then is what's used then to toast your toast, so that you can have your breakfast. Same if you want to boil a kettle, for example, you will have the electrical energy will heat up the element that's inside the bottom of the kettle, and that heat energy will boil the water, and then you have hot water to make your cup of tea. But all the time you have energy be converted from one form into another. And that's essentially what power is. So basically power is, for example, like electrical energy being converted into other forms of energy. Or another way to kind of think about it is it's the amount of electrical energy that an appliance needs in order for it to do some useful work, like cook toast, like boil water, think of all the other electrical appliances that you have in your house. So energy then is the ability to do work. Coulomb, if you think about the Coulomb, basically it's the charge on a huge number of electrons, 6.2 multiplied by 10 to the power of 18. So that's just the way, it's like saying a dozen eggs, instead of saying you say you have a coulomb, for example, of electrons. Okay, it's more related to the charge that's on the electrons, but that's kind of like the way to kind of think about it in your mind. Voltage then is it's joules per coulomb. So for example, when these electrons are moving, the higher the voltage, okay, that means the more energy those electrons have. So for example, if we have electrons moving in here and they're moving in with really high energy, and if they hit these atoms at much harder, what's going to happen is it's going to cause them to vibrate even more, and it's going to make even more heat energy. So the harder these electrons hit the atoms, for example, that are in the conducting material, the more energy that's going to be changed from one form of energy, electrical energy, into another form of energy. So that's a way to kind of think about like voltage. That's essentially what voltage is doing. Current then is just the flow of electrons. So and specifically, if you were to think about every single second, it's the number of coulombs of electrical charge that's passing the point every second in the conducting material. So that's a way to think about amps. And then watts then is like a combination of voltage and current. So it's the amount of electrons that are moving through the material, the force at which they're moving through the material, and then the amount of energy that's being converted from one form into another every second. That's power. Okay, so power is just basically voltage multiplied by current, and the unit that we use is the watt. So how do you think about the watt? It's joules per second, or another way to think about it is it's the amount of energy that's been changed from one form into another every second. So for example, if you have a filament bulb, it's the amount of electrical energy that's been converted into light and heat energy. If you have, for example, a heater, it's the amount of electrical energy that's been converted into heat energy. That's essentially what power is. And we measure power in watts. So the bigger the wattage of the appliance that you're looking at, the bigger ability it has to convert energy from one form into another. And another way to kind of think about it is the bigger the wattage, the more electrical energy that appliance is going to need in order for it to do some useful work or to do what it's supposed to do. So if we have a look, so when you look at most electrical appliances, if you have a look on the appliance, it'll tell you, for example, the wattage of the appliance. So if we take, for example, this electric bulb here, so this electric bulb is a 10 watt electric bulb. So that means that it's going to convert 10 joules. So it's going to convert 10 joules of electrical energy per second. Okay, so it's going to use up 10 joules of electrical energy every second. Okay, so that's a way to kind of think about wattage. Okay, so it's 10 watts, so it's going to use this 10 joules of electrical energy every second. Now, if we have a look at some different appliances that we have, so in this table here, so we can see a lot of the times as well, what you will see on appliances is this here, what's known as a kilowatt. Okay, so it's known as a kilo, so K and then watt. So kilowatt basically is, so 1 kilowatt is equal to 1000 watts. That's what this kilo means. So similar to, for example, 1 kilogram, kg, is equal to 1000 grams. Well, when we're talking about kilowatts, 1 kilowatt is equal to 1000 watts. And generally when we're doing calculations, we work with kilowatts. So 1 kilowatt is basically an appliance's ability to take 1000, so 1 kilowatt, another way to kind of think about it is it's converting 1000 joules of energy per second. Okay, so that's a way to kind of think about, like, a kilowatt is basically, what it's doing is it's converting 1000 joules of energy from one form of energy into another every second. So it might be taking electrical energy and turning it into heat energy every second, 1000 joules. So if we have a look at some of these appliances here, then it gives us an idea of like the amount of energy requirements that are needed for to run some of these common household appliances. So if we take a TV, for example, so TV takes about 0.2 kilowatts of energy to run. So, and then when you're paying, for example, if you're paying for electricity, you're paying for the the amount of energy that you use every second. So that's essentially what you're paying for. So when I looked this up, so electricity was costing roughly about 29 cent per kilowatt. So if you were to take, for example, a TV, it takes about 0.2 kilowatt hours. So if you were to, for example, to run a TV for 4 hours, it's costing 23 cent. So it costs about 6 cents per hour. So therefore it's costing about, in 4 hours, you're talking about 23 cents. So if you're running a TV, that's just for a TV every single day. Okay, so imagine if you might be using it for more than 4 hours. If you're to take a laptop, for example, it uses about 0.1 kilowatts. That's how much energy it needs in order to run. So that costs roughly about 3 cents per hour. And if you were to run that for 8 hours, it's costing you roughly about 16 cents. And similar to a kettle, if we look at a kettle, so it's roughly about 2.5 kilowatts. It costs, so if you were to take to run it for an hour, you would be talking about 73 cents. So if you were to boil a kettle for 10 minutes, for example, that would cost you about 12 cents for 10 minutes. So that's kind of just giving you an idea of what we mean by power and how we pay for power and essentially what power is. So power is the ability of the appliance to take electrical energy and convert it into some other form of energy per second, and it's measured in watts. So power then, so just to kind of to zoom back out then and look at it from a more higher level, so power is how quickly energy is converted to other forms, how it's changed from one form into another. The more powerful something is, the quicker it's able to convert energy from one form into another. So power is measured in watts. Higher power electrical devices use a lot of electricity very quickly. So depending on, it'll tell you the wattage on the appliance, the bigger the wattage, the more electricity it'll use. And they can be expensive to run as well because you pay for the amount of energy that you use per month. So if we have a look at this, for example, so if we were to take like 3 different types of bulbs, so if you have one bulb that's a 40 watt bulb, another bulb is 60 watt, and another one's 100 watt, we can see that as we move from left to right, it takes more and more electrical energy to light these bulbs. So increased power means more light production. And another way to kind of think about it is the more powerful the bulb is, okay, the more electrical energy is being converted into light energy. So for example, if we take a 100 watt bulb, it's going to shine much brighter. It's going to be much brighter than a 40 watt bulb, for example. But the other side of that is that it's going to be more expensive because it's going to use a 100 watt bulb, it's going to use way more electrical energy than a 40 watt bulb. So if we want to calculate power, we generally need the current and we need the voltage. So electrical power is calculated by multiplying current multiplied by voltage. So we have current here, which is represented by I, multiplied by voltage. So if we have a look at these two calculations here, so what is the power rating for a filament bulb that uses 0.272 amps connected to a 220 volt main supply? So what we do is we just multiply these by each other. So the power is going to be 0.272 multiplied by 220, and that's going to be equal to 59.84 watts, or if we just round it up, it's equal to 60 watts. Now, if we take another type of bulb, which is an LED bulb, what is the power rating for an LED bulb which uses 0.045 amps connected to a 220 volt main supply? So if we multiply these by each other, 0.045 multiplied by 220 volts, that's equal to 9.9 watts. So what we can see here is that if we compare these, so a filament bulb and an LED bulb, we can see that LED bulbs are way more energy efficient. So that means that they use up far less energy than filament bulbs. So filament bulbs, they take 60 watts of power to make them run, whereas an LED bulb we can use, so it's 9.9 watts of power. So therefore, if we look at the difference of these, like the LED bulbs are way more energy efficient. So when you look at, if you look at any of your electrical appliances in your home, you'll see on the back of it, it'll always tell you, for example, the power, the wattage on it. So for example, if we have a look at these two here, so this top one is just a normal room, like a room heater. Okay, so like one of those bar ones, and then this one down here is like a fan heater. And what we can see if we look at the difference in the power, the wattage, so this is 2000 watts, okay, and then this one here is 120 watts. So electrical devices have power rating labels that provide information on the voltage and power usage of the device. Okay, so the bigger the wattage, the more power the device needs. Ovens, toasters, and heaters have high power ratings and need a large current and have higher power ratings. Okay, so they consume a lot more electrical energy. Power ratings should. So when you are comparing, for example, the power demands of a particular appliance, you always look at the wattage. And one of the best ways to do it then is to take the wattage and convert it into kilowatts. So remember, 1 kilowatt is equal to 1,000 watts. So therefore, if we take 2,000 watts, that's going to be equal to 2 kilowatts. And if we take 120 watts, that's going to be equal to 0.12 kilowatts. So if we compare these two heaters to each other, we can see that the room heater is going to use it's going to need far more power in order for it to work. It's going to need way more electrical supply, whereas the fan heater it's going to consume less power. Okay, so you have 2 kilowatts versus 0.12 kilowatts. So that is power, and that is how you go about and you measure power and how you go about calculating power.